Hey guys, one new thing that we're going to deal with is we're going to talk about buffers. Buffers are solutions that resist a change in pH even when an acid or base is added. The most common types of buffers we're going to come across are a weak acid and its conjugate base salt. So like a mixture that would have hydrofluoric acid and then sodium fluoride. So you have both the acid and the fluoride ion. We're also going to come across where the buffer is a weak base and its conjugate acid salt. Something like ammonia and then ammonium chloride that yet again has the base ammonia and then the ammonium ion. So what happens whenever we have a buffer? It has something that can react with both acids to neutralize them, and it will react with bases to neutralize them as well. So whenever we have the mixture of acetic acid and a mixture of sodium acetate, in that mixture we're going to have acetate ions, the acetic acid, hydronium ions, and sodium ions that can all interact in different ways. Same thing if we do a buffer with the base. If we mix the ammonia and ammonium chloride, in that solution, you're going to have the ammonia molecules, ammonium ions, chloride ions, and hydronium ions. So everything will be able to interact with different types of particles. So talking about a buffer itself. So we might be given a nitrous acid sodium nitrite buffer. And I apologize, I'm having to write using my laptop, so it may not be fully clear. But remember, nitrous acid is HNO2, and the sodium nitrite is going to contain the nitrite ion, which is NO2 negative. And the deal is it's always going to end up producing water in some way whenever it reacts with either an acid or a base. So let's look at what happens if we add an acid to it. If you add an acid to a buffer solution, it will be consumed by the base part of that buffer. So the base part of our buffer is the nitrite ion. So what happens is the nitrite reacts with the acid. So we're going to put H3O plus since that will be in any acid that gets added. And remember we said that this is always going to produce some sort of water. So the hydrogen from hydronium is going to be absorbed by the base. So it will make the nitrous acid. And water. So it neutralized the acid particles, producing that weak acid that's also part of our buffer. And then yet again, we said it's always going to produce water. So whenever you have an acid added into your buffer, it's going to react with the base part, producing a weak acid and water. On the flip side, if we add a base to our buffer solution, it will be consumed by the acid. So our acid is the nitrous acid, the HNO2. That's going to be added to our base, which is going to have hydroxide. And this will produce a weak base, so that hydrogen is going to react with the hydroxide to produce water. And what's left over is our weak base, which was the nitrite ion. So you'll end up with both ions or molecules that were part of your original buffer system that are being created whenever it's neutralizing any added acid or base. And yet again, it will always, always produce water. So here's an example of a buffer solution. We have the weak acid, which is the HAN, with the anions that are just the AN negative. If we add hydrogen from an acid, remember hydrogen will react with the base, so that will react with the anion part to produce more of that parent acid. But it still neutralizes it. It still didn't use up all of the base. So that's how this can act as a buffer system. Whereas if we add hydroxide from the strong base, it will react with the acid, the HAN, and produce more of the anions and water. So a buffer tends to occur where you have more equal concentrations of the weak acid and conjugate base. So that's our middle image. After you add hydrogen, it's going to shift towards the left where you have more of that parent acid, less of the anion. If you add base, it will shift more towards the right where you have more of that anion, less of that parent acid. But it still is not going to change the overall pH because you don't have an excess of hydrogen or hydroxide at this point in time. All right, so whenever you're given an ammonium chloride buffer, so this is one where we have a base and its conjugate acid. Remember, ammonia is NH3. Ammonium is NH4 plus. And this will react the same way. Whenever we add an acid, it's going to be consumed by the base. So remember, our base here is the ammonium, so the NH3. When that reacts with acid, which we said was represented by H3O plus, remember we said that's always going to produce water whenever it's in a buffer solution. And we said that the excess hydrogen and hydronium reacts with our base, ammonia, to produce the ammonium ion, the NH4 plus. Same is true for the flip side. If we add a base to our buffer, it will react and be consumed by the acid. So remember, our acid here is the ammonium ion, the NH4 plus. That reacts with a base, which we're representing as hydroxide. It's always going to produce water. And it will produce, so a hydrogen from ammonium reacts with the hydroxide to produce water, leaving us with ammonia, which is NH3. So that's how buffers work, and that's kind of the equations we're going to deal with buffers. We're going to deal with the math a little bit later. But buffers are going to be any solution that has something that can consume hydrogen ions, so anything that is considered to be basic, and it also has to have something that can consume hydroxide ions, so something that can be acidic. It has to have both in order to act as a buffer. If it only has one, it is not a buffer. It must have both. So there are other exceptions. of solutions that can be a buffer, even if it isn't a weak acid with its conjugate base or a weak base and its conjugate acid. Some ways that you can have this is you'll have an amphoteric ion. So remember, something that's amphoteric is something that can gain or lose hydrogen ions. So examples are stuff like the hydrogen carbonate ion. Sorry, that's supposed to be an H. It cut off the top. So the hydrogen carbonate ion can lose the hydrogen or gain an additional hydrogen to be carbonic acid. Same thing with this hydrogen phosphate ion. It has the ability to lose one of its hydrogens or gain another hydrogen. So that's a sample of something that can be a buffer by itself, because that one ion can act as an acid and a base. Another example where you have a buffer, even though it's not a weak base with its conjugate acid, is if you have a salt that is not going to produce any spectator ions. So something like ammonium nitrite. All of this will cancel out, and we're not going to have any spectator ions. So what happens is, if you kind of split this down the middle, the ammonium ion is able to react with hydroxide, and ammonium hydroxide would be a weak base. The nitrite ion is able to react with the acid and produce nitrous acid, which is yet again a weak acid. So both ions are able to produce some form of acid or some form of base. So here's a chart that has a little bit of everything listed together. We have the types of buffer solutions. So we already went over a weak acid with its conjugate base in that first column. We went over how it reacts with hydrogen, how it reacts with hydroxide. Yet again, both of them are going to produce water. We have a weak base and its conjugate salt. So that was our ammonium chloride. The salt without the spectator. Here we used ammonium fluoride. So the ammonium is our acid, fluoride is our base. So the base can react with hydrogen, producing hydrofluoric acid, excuse me. The base can react with our acid, producing water and ammonia. If you have a salt with that amphoteric ion, so that hydrogen carbonate like I listed, that one ion is acting as both your acid and base. It just depends on if it reacts with acid, it will produce carbonic acid. If it reacts with a base, it will produce water and then the carbonate ion. But yet again, that one ion can act as both the acid and the base. We'll be doing a little bit more with buffers, but hopefully this gives you more of an understanding of what they are.